Let's look at lenses, diverging lenses. This description is given based on how the rays behave. Converging lenses generally cause the rays to move together and converge, and a diverging lens would cause the rays to move apart or diverge. So let's look at converging first. Converging lenses are like the lens in your eye or a magnifying glass. They can also be found in microscopes and telescopes. A converging lens is generally shaped where it has two convex sides, and through the middle we call this the midline. And typically the rays that pass into the lens will converge. And if all of these initial rays are parallel, then they will converge at the focal point. Now for a converging lens, there is a focal point on the right side of the lens, and there's a focal point on the left side of the lens. And the focal point for converging lenses is always considered positive by convention. Now, just like mirrors, we can use the equation 1 over dO plus 1 over di is equal to 1 over f to find the position of our image, or the focal point if we know the object position and the image position. A converging lens will create a real image when these real rays converge in one place. So, for example, the light that passes through your eye lens will converge on your retina. The image will actually be upside down, and your brain interprets it and turns it right side up for you. Pretty amazing. So in this example, where is the image formed if the object is 4 centimeters in front of a converging lens with a focal length of 2 centimeters? Let's look. So if 1 over dO plus 1 over di is equal to 1 over f, then we'll have 1 over 4 plus 1 over di is equal to 1 over 2. Di would be 4 centimeters. Now what does this mean? This means that if we have our converging lens, and here is our parallel principal axis, the focal point is, there's a forward focal point and there's a behind focal point, because we've got this curvature is creating this focal point and this curvature is creating that focal point. And our object, though in this case, was twice as far from the focal point, so it was out here at this position here. Now if we follow the rules for drawing a ray diagram, we would have an arrow, a ray that goes parallel and then through the focal point, and then through the front focal point, and then out parallel. And you may notice that these two rays appear to cross over at about twice the focal point. And so this is our image distance, this is our di, and because our object was at 2 times f, then our image is also at 2 times f, and this positive value for our 4 centimeters location means that the object, or the image, is real and it's inverted. And then we can determine the magnification by using the same magnification equation that we have used before for our mirrors. The magnification is negative di over dO. So negative. Now di was a positive 4, and dO is also a positive 4. And so we get negative 1. So that negative tells me that it's inverted. And the positive image position tells me that it is real. And real images are formed on the other side of the lens. So think about how your eyeball works. Your eyeball has a lens that's shaped like this convex lens, and that lens in your eye, and outside of your eye, out here, there may be a tree. And the light rays from the tree pass into your eye and they converge. They converge on your retina, this screen in the back of your eye. And then your eye sees this tree upside down as a real image projected on the screen behind your eye. So this retina behaves like a screen, just like when you go to the movies. If you watch a film projected on a screen, the film is actually fed in upside down so that you see it right side up. So let's say if a converging lens has a focal length of 4 centimeters and the object is 1 centimeter in front, where is the image formed? So we're going to use the same equation that we've used before, that 1 over dO plus 1 over dI is equal to 1 over the focal point. So in this case, our object is 1 centimeter in front. So that's 1 over 1 plus 1 over dI is equal to 1 over the focal length. So 1 over dI is equal to 1 over 4 minus 1 over 1. So then 1 over dI is equal to negative 3/4, and that means that dI would be equal to negative 4/3, or negative 1.33 centimeters. So this is a negative image position. This negative tells me that this must be a virtual image. Now, where is the image formed? Where would the negative be? So let's look at the setup of this problem. So we have our axis and our lens. And our lens has a focal length of 4 centimeters. So here's our 4 centimeter focal length. And our object is 1 centimeter in front. So there's our object. Now, the positive image distance is on the other side of the lens. So if I was looking for the image and the image was positive distance, then it would be over here. But the image distance is negative in my calculations. So that means my image is going to be formed on the same side of the lens as the object. So if I use some ray diagrams, I've got a parallel and then through the focal point. And then we have another ray that is in line with the front focal point and then goes out parallel. Now these rays over here will never converge, but these rays appear to converge in front of the lens. So let's call this the front, and this is the back. So if you're the observer and you have an eyeball here, so here's your eyeball, and you're looking at some object here, you're going to see that that object appears to be formed at this place right there. So that image is virtual. It's not really there because these rays are virtual rays. It is a upright image, which also will support the fact that it is virtual, and it's enlarged. So this is a case where my converging lens behaves like a magnifying glass. Diverging lenses are a lot like the convex mirror, but our diverging lens has two concave looking sides there, and we have a principal axis. So because a diverging lens is this side right here has a focal point here, and this side right here has a focal point there, we call those negative focal points. So by convention, the rule is that a diverging lens has a negative focal point. So where is an image formed if the object is 4 centimeters in front of a diverging lens that has a focal distance of -2 centimeters? So let's do this using our same equation for our lenses. 1 over DO plus 1 over DI is equal to 1 over F. It's very convenient that the equation for lenses is the same as the equation for mirrors. So 1 over DO. DO is 4 plus 1 over DI is equal to 1 over -2. Don't forget that negative sign. Even if you're not given the negative sign in the question, if it is a diverging lens, we must use a negative sign in front of the focal distance. So then 1 over DI would be equal to 1 over 2, negative 1 over 2, minus 1 over 4. 1 over DI is equal to -3 over 4, and then the inverse DI would be equal to -4/3. So again, this DI would be -1.33 centimeters. So what does this mean about the image location? If here is our principal axis and here is our diverging lens, and our object is out in front at 4 centimeters, and the focal point is at 2 centimeters, then we would have a ray that is parallel, but then it diverges in line with the focal point. Then we have another ray that's heading towards this other focal point, but when it hits the lens, it changes and goes out parallel. And so this ray appears to be coming from back here. So if we zoom way in, our image would be formed here. And it is virtual, it's upright, it has a negative image position, it's virtual, it's upright, and it's reduced. It will always be reduced. This lens is a lot like a convex mirror in the sense that it always produces a virtual, upright, reduced image.